So hello friends, again let's start the second lecture on advanced thermodynamics. In the first lecture we had a basic introduction to thermodynamics. We looked at the chronology in which the various laws of thermodynamics evolved, and we also looked at the introductory definitions about object isolation, and we just introduced these terms. So let's go back to that slide and start from where we left. Okay, so let me share that slide with you. So yeah, so we started with this slide, in which we talked about thermodynamics is a science which deals with objects and their interaction in the presence or absence of contact. And we said that all of these red terms we will define and we'll understand. So we talked about observing an object. When the object is observed, it needs to be at least notionally isolated, if not perfectly isolated, because perfect isolation in reality becomes impossible. So you need to leave it undisturbed for some time in order to be able to observe it, so that you get what its property is. And while you are doing that, in order to observe it correctly, the object has to be in equilibrium within itself, is what we actually talked about. So we started defining these quantities one at a time. So the object is that part of the world around us which we would like to study, and surroundings is the part of the world in the vicinity of the object, not necessarily the rest of the universe. And isolation is when there is no form of interaction with other objects or surroundings. And we said that perfect isolation may never be possible, so we normally resort to saying that, okay, if the changes are comparable to or smaller than the least count of the instrument or the time constant of the instrument, the changes are slower than the time constant of the instrument, and so on. We make such approximations and say that, okay, then we can notionally consider it to be isolated for observation. So that's the point that we conveyed in the last class. So now we'll continue with the discussion that we started. So we'll talk about the next term, which is equilibrium. We discussed about this in the previous class. We said that when there is no spontaneous change that's occurring in the object during the observation, then the correct observation is possible. So for example, if I gave the example of a cup of coffee whose temperature I'm trying to measure, so I said, okay, if I have a thermometer which has a time constant of 2 minutes, it says that I have to keep it in that medium in which the temperature is being measured for about 2 minutes in order to allow the thermometer to read the correct value of the temperature. So then I call the time constant of the thermometer is 2 minutes. Over these 2 minutes, if the temperature of the cup of coffee is changing rapidly, in the sense that if the temperature of the coffee is changing at something like 2 degrees Celsius per minute, so in 2 minutes the temperature would have changed by about 4 degrees. So the temperature that you measure by the thermometer is not one value, but it is continuously changing values, and what you read you would not know is the temperature at what instant. Okay, so then it's not a proper observation. On the other hand, if you have such a temperature that is changing at about 4 degrees Celsius per minute, then you would need a thermometer whose time constant is, let us say, 1 second or 2 seconds. So in 1 second or 2 seconds, if the temperature is changing at 2 degrees Celsius per minute, so then it is 2 degrees in 120 seconds. So it is 1 by 60 degrees per second. So the temperature would have changed only by 1 by 60 degrees in 1 second. So if your time constant of the instrument is 1 second, then it would have measured the temperature within that accuracy, and therefore you can neglect the change that happened in that particular time period, because in the best case the thermometer itself might have a least count of, let us say, 0.5 degrees or 1 degree, in which case the change that is happening in that period is negligible. So we could consider this to be a quasi-equilibrium state, or an equilibrium which is notionally Correct. So in reality, we need to basically deal with all such approximations and idealizations. But in thermodynamics, when we say we want to measure the temperature of an object, we need to leave it alone, completely isolate it from interactions with the surroundings, and then observe it. And the instrument with which you observe it should not also take away or change the property that you are measuring. So that's the example that I was giving you last time, that if I have a cup of coffee whose temperature I am measuring, and I put a thermometer, and the thermometer is so heavy that it absorbs 1/4 of the energy that was there in the coffee, then by the time the thermometer reaches the temperature of the coffee would have cooled down to the temperature of the thermometer, or part of the way, and therefore the reading that you are taking would be wrong. So all of these are factors in reality, but in the case of thermodynamics, when we talk about equilibrium, we say that in order to observe any object, in order to make any measurement of any object, you need to have it isolated from its surroundings and in equilibrium with itself. In equilibrium with itself, I mean that the temperature, if I'm measuring temperature, for example, the temperature within the object, throughout the object, anywhere that we see, should not be different from one another. So if I measure the temperature closer to the wall of the cup or in the interior of the cup, the coffee temperature should be the same or negligibly different in practice. Right? So that is basically what we understand by equilibrium of an object within itself. Yesterday we also talked about the equilibrium between objects. That we will come to later. So this is another example. Suppose I am measuring the temperature of a slab with dissimilar temperatures on the two surfaces. If I isolate this, okay, so initially let us say there is a slab who has temperature T1 on the left surface and T2 on the right surface, and there is a variation in temperature in between. Now if I try to observe the temperature at any point in this, at this point in time, then you would have different temperatures in different locations, and therefore the slab is not in equilibrium in itself. Now if I isolate it from the surroundings, so I insulate both the surfaces and leave it for some time, then the higher temperature region would cool down by transferring heat to the lower temperature side. The lower temperature would warm up by taking that energy, and eventually the entire slab would come to the same temperature. Then any measurement that I make would be the correct temperature of the slab. So this is basically what I mean by thermal equilibrium of an object within itself. So the correct temperature is obtained when the slab attains uniform temperature throughout, that is, it attains thermal equilibrium. This is different from the thermal equilibrium with other objects or surroundings. That is, if an object is left to itself in the surroundings for a long period of time, it comes to thermal equilibrium with the surroundings. Or if I have two objects, if I put them close together and isolate them from the rest of the surroundings, then each object would actually come to thermal equilibrium with the other. So that is thermal equilibrium between objects, and the thermal equilibrium that we talked about in the first case was the thermal equilibrium of an object within itself. Right? And since all characterization needs equilibrium, any measurement would actually need equilibrium, because I cannot keep measuring things which are running away. So I need them to be in equilibrium at least for the duration of the observation. Right? So if I'm, for example, measuring the change in temperature of a slab with time, then what I need is that I need an assurance that at any instant when I'm measuring the temperature, the instrument that is measuring the temperature is in equilibrium with the point whose temperature it is measuring. And that can only happen if the time constant of that object is so short that even when the temperature of the object is changing, the temperature of the instrument also changes along with it as quickly as the change in temperature happens, or very, very quickly after that, so that you can assume that the probe temperature or the thermocouple temperature or the thermometer temperature is the same as the body temperature practically at all times. So this is something we call it as quasi-equilibrium, because it's not necessarily exact equilibrium, but then there is a small lag with which the instrument follows. We at least need the quasi-equilibrium to be able to make realistic measurements. Right? So that's the thing that I was talking about. The next thing that we are going to talk about is properties. So I was all this while giving an example of measurement of temperature. The temperature is the property of an object because it indicates at what relative degree of hotness or coldness. So it's basically, in some sense, a representative of your touch sense. So by touching an object, you can say whether it's warm or cold, but this is a relative picture because you cannot absolutely say that an object is warm or an object is cold, but you can only say it is warmer than my hand. So if I put my hand on it, if it feels warm, then it's warmer than the body temperature or my hand temperature. Similarly, if I feel it cool, it's cooler than my body temperature or my skin temperature. So it's actually a relative picture. So that is the temperature that we are presently dealing with. We will be dealing with a more absolute quantity of temperature as we go on in the course of thermodynamics. So right now, let us understand the temperature that we talked about as what we call as an empirical temperature or an experimentally observable temperature, which is basically a degree of hotness or degree of coldness, which is a relative picture compared to the absolute temperature, which we will come to when we study second law of thermodynamics. So in thermodynamics, temperature therefore is a property. Even empirical temperature is a property. Likewise, you have various other properties. So the cup of coffee that I talked to you about as an example, what are the other properties does it have? It has a mass, it has a volume, and therefore the mass divided by volume, it has a density, or the volume divided by mass, so it has a specific volume. It also has the temperature. It is kept at a certain pressure, let us say, in the atmosphere. So there are several properties that an object is characterized by at any given point in time. So what is a property? It is actually nothing but a macroscopically observable characteristic of an object. So any object, you can observe the macroscopic characteristic of that object either through one of your senses, which is a relative thing, you cannot quantify it. But if you use an instrument which is repeatedly calibrated against a certain standard that we have set, then we can actually assign a value to a property. Okay, so that is normally what we call as property of an object. So at any instant, there are several properties that characterize an object. That's what we just talked about with the example. And some of these properties are interdependent, and some of this can be varied independently of the others. This is something that also we understand. We said that mass, volume, density, mass divided by volume equal to density is a definition, and therefore two out of these properties could be independent of each other, but the third would normally be dependent on that. But one of them could well be the characteristic of the object. That is, if I take, let us say, 1 kg of water at a certain pressure and temperature, then it would always have a certain volume. So then the volume per unit mass, or the specific volume, or the mass per unit volume, which is the density, at that pressure and temperature is a characteristic. So now the density depends on pressure and temperature. Okay. So if I have a certain mass at a certain pressure and temperature, then the volume is automatically determined. So there are some properties which are dependent on the other, and there are some properties which can be independently varied of the other. Say, for example, I can have a kg of water. I can heat it so its temperature can go up. I can cool it so its temperature can go down without changing its pressure, without changing its mass, without changing its volume, and so on. So there are some properties which you can vary without changing the others, and there are some properties which you, when you vary, they automatically change the other properties. So now the properties that can be independently changed of the others are called orthogonal properties. The orthogonality property is something that comes from mathematics, but you can understand it by, let us say, the perpendicular axis of a graph, the x-axis and the y-axis. So if you change x, you can keep the y constant and change x, and similarly if you change y, you can keep the x constant and change y. So these two axes, when they are perpendicular to each other, we say that they are orthogonal axes. So if two properties, one can be varied by holding the other constant, then these two properties are orthogonal. Okay? And for a given object, the number of orthogonal properties that characterize it would actually be fixed, dependent on the kind of interactions that that object goes through. So we will come to that when we talk about that. Right now we'll say that we can define a system with respect to an object. We have been talking about a simple object so far. When a system is constituted by many objects, then it can be divided into subsystems. Okay. So when I divide an object or a system into subsystems, there are some properties of the object which are the same in all the parts. Say, for example, if I take let's say 1 liter of water and divide it into 2 half-liter volumes in 2 vessels, What remains constant in this? The density of the water in both the vessels is the same. The pressure of the water in both the vessels is the same. The temperature of the water in both the vessels is the same, and so on. But then what happened to the volume? The volume got divided. Okay, so there are some properties which remain the same between the subdivided components of a system, and there are some properties which do not get subdivided but remain the same. They remain the same when you divide the object. So these properties which do not change because of dividing an object into sub-objects or system into subsystems are called intensive properties, and those which get divided are called extensive properties. For example, the density, pressure, temperature, etc. are intensive properties, and volume, surface area, etc. are extensive properties. Now, this definition is not a very fundamental definition, because if I take the example of two batteries in series or parallel, that's a system where you can have voltage and current. In one case, the voltages get added when the batteries are put in parallel, and if I put the batteries in series, it's actually the current that gets added. So when I divide, it's a current that gets divided in a series system, and voltage that gets divided in a parallel system. So it's not a fundamental definition. It also depends on the way the system is, but it's a useful way of defining things, intensive and extensive properties, and that's how we define this. Okay. Then we define what is called the state of an object. The state of an object is constituted by a combination of its properties. There are multiple properties that characterize an object. So a set is uniquely defined, a state is uniquely defined by a set of all its orthogonal properties. Okay. So the properties that can be independently varied of each other, they together constitute the state of an object. So the object is in equilibrium at each of its observable states, and therefore all the states are called equilibrium states, in the sense that whenever I measure any property, I measure it only when the system or object is in equilibrium within itself, and therefore each of these states is constituted by multiple properties which have been measured when the object is in equilibrium within itself, and therefore the states are normally known as equilibrium states. Now, when the object changes from one state to another state, it is said to undergo a process. So initially, let us say the object is at one state which has a certain set of properties, and after some time it gradually transitions to another state and goes to equilibrium at that state. So its transition from one equilibrium state to another equilibrium state is called a process. Okay. So we have all understood about processes. Suppose we take the same example of a cup of coffee which is initially at, let us say, 75 degrees Celsius in a cup. I have just left it on the table and allowed it to stay there for half an hour. After half an hour, the temperature of the object would have come down substantially from the initial 75 to somewhere close to the room temperature. So suppose the room temperature is 30 degrees Celsius. The coffee might be at a certain temperature like 32, 33 degrees Celsius. So it is still not in equilibrium. You leave it for enough time, then it goes to equilibrium with the surroundings and comes to the same temperature as the surroundings. Then this equilibrium state is at 30 degrees Celsius. The initial equilibrium state was at, let us say, 75 degrees Celsius. So between these two, there has been a change. So the system or the coffee has undergone a process, and this process has happened when the pressure of the object is the same. So it's a constant pressure cooling process of the coffee. So that is the process. So processes can be defined on the basis of what is kept constant, what is varied, and so on. And then you get various different kinds of known processes. There can be processes whom you cannot name also, but when there is a change from the initial state to the final state, it's called a process. And if after a sequence of processes an object regains or returns to its initial state, then it's said to have executed a cycle. So if I plot on the state space, so let us say two independent properties define the state of an object. So I have an x-axis which is one property and y-axis another property. So I can mark the state of an object on that graph. Okay. So now if I go from that initial point, tracing a path in which both x and y keep changing, and then finally I come back to the same initial value of x and y, that's the same initial state, then I complete a circle, or I complete a closed polygon, and this is said to represent a cycle in the state space. Okay. So now we have talked about individual single object, its property, its state, and its process, and the process that completes the cycle. Now the next thing that we will do is what happens when two objects are brought to close to each other and they are allowed to interact by a certain mechanism. Okay. So we'll take examples of this. Right now it might sound a little bit abstract, but we can take examples of this. So we'll talk about what is called interaction. So when two objects are connected together by a device, they interact. So let us take an example. So let me move on to my whiteboard so I can draw something and show it to you. I hope you should be able to see the whiteboard right now. So suppose I have one object, which is, let us say, a spring, and I have another object which is also another spring. Okay. So let us say this is object 1 and this is object 2. They have their own initial natural lengths. Okay. And these two objects now are independent. They are not connected to each other. Suppose I attach an eye here and a hook here and pull this down, pull this up, and connect the eye and the hook together. So then I'll have this and this. Now these two objects are connected to each other. Okay. So each one of them had a certain initial length. So then one object exerts a force on the other depending on the initial extent of stretch that is there in each of the springs, and then eventually they go to equilibrium. Okay. So suppose this spring was stretched and this spring was also stretched. Each of them would then exert a force which would be in a direction to restore its initial length. So if object 1 exerts a force F1 and object 2 exerts a force F2, then there can be three states here. F1 is greater than F2 and F1 is less than F2 and F1 is equal to F2. Okay. These are the three possibilities that are there depending on how much we stretched one, how much we stretched two, and what the spring constant of the first one is, what the spring constant of the second one is. Depending on that, we would have F1 exceeding F2 or F1 less than F2 or F1 equal to F2. So what happens if F1 is greater than F2? Then the spring number 1 is able to pull the spring number 2. So the movement of the point of interaction would be upwards because F1 is pulling it upwards. So then if I call the length of this object as x1, then delta x1 is less than 0 because x1 decreases, right? And if what happens if F2 is greater, that is F1 is less than F2, then the delta x1 is greater than 0. And what happens when they are equal? Then delta x1 will be equal to 0. Okay. So these are the three kinds of states or three kinds of cases that can arise when I make these two objects interact. Okay. So this is the example of a spring interacting with another spring. Okay. So now if I go back to the PowerPoint slide and try to look at the definition, it will look less abstract. So let's move there. Okay. So when two objects are connected to each other by a device, in this particular case the device is the eye and the hook, the spring hook. This is one example. I can give the other example of galvanic cell and capacitance with connectors. I'll give you that example very soon. So there is a condition of interaction that characterizes this interaction. What is the condition of interaction? Let us go back to the diagram again and try to understand it there. Let's go back to the whiteboard and take a look at it there. Okay, so the condition for interaction now will be that if x2 is the length of the second spring and x1 is the length of the first spring, then x1 plus x2 is constrained to be equal to this distance between the two planes to which the springs are connected. Initially, when the springs are not connected, this is x2 and this is x1, they are independent of each other. But when the springs are connected to each other, they are constrained to change in such a way that x1 plus x2 is always equal to this h. Okay, so the condition for interaction here will be x1 plus x2 is equal to h. Or in other words, if I differentiate this, I'll say delta x1 plus delta x2 equal to 0, because the h doesn't change. So when there is an increase in x1, there is a decrease in x2, and then when there is an increase in x2, there is a decrease in x1. So that is basically the thing. So we can express the condition for interaction either as x1 plus x2 equal to h, or delta x1 plus delta x2 equal to 0, or delta x1 equal to minus delta x2. That is what we understand by the condition for interaction in this particular case. So there is actually a relationship between the variable that is affected by the interaction. The length of the spring is the variable that is affected by the interaction, and what causes the interaction is the force of the springs. So you now have an effect and a cause. The condition for interaction is the relationship between the effect variables, and the condition for equilibrium will be a relationship between the cause variables, in which case the F1 equal to F2 causes the delta x1 to 0, and that is a condition for equilibrium. Okay, so we'll stop this lecture at this point. We are already about 25-26 minutes through this lecture, so I'll stop this lecture here, and let's continue the topics in the next lecture. Okay, stop it here.